So last lecture we talked about normal distribution, which describes the population of large data sets. So when we say normal distribution, we immediately associate with the PDF, the probability density function or probability distribution function, f of x dx equal to sigma square root of 2 pi exponent of minus 1 half x minus mu over sigma squared dx. Now, can somebody tell me what f of x dx itself represents? What is f of x dx? This is called the probability distribution function. Probability distribution function. That is, I'm talking f of x is the probability distribution function. So if I say here is f of x, okay, and I'm considering an interval dx, and I consider f of x dx, what does that represent? First of all, from the graph, what is f of x dx? If this value is on an average f of x, what is f of x dx? This is the area between x and x plus dx. Area under the curve, right? And I told you this f of x is called probability distribution function, essentially saying f of x dx is the probability that x takes a value between x and x plus dx. I mean, I'm just recapping what we did so far. Otherwise, today's lecture will look very discontinuous. And if I write a to b f of x dx, what does this represent? This is area under the curve between x equal to a and x equal to b. What is it? What is it equal to? So if I say this is a, this is b, what does this area actually represent? Okay, since nobody would say, it's all in your notes, I hope. This is the probability that x takes values between a and b. Okay, so I posted some mock exams where you are asked to calculate x taking values between certain range, which is a to b f of x dx. Okay, and we also saw what is called as the cumulative distribution function. CDF, which is minus infinity to x f of x dx. Minus infinity to a, let's say. This is probability of minus infinity less than x less than or equal to a. So we'll write this. We'll call this f of a. So this is the probability. This is the probability that x takes values from minus infinity to some arbitrary value. So this is all the area to the left of x equal to a. To the left of x equal to a. All right. So if I want the area between some a to b, using this notation, how will you write this? This is integral a to b f of x dx. Can I rewrite it minus infinity to b f of x dx minus infinity to a f of x dx? Can I write it this way? I'm splitting this integral to call it whatever b is minus infinity to b minus infinity to a. So this is nothing but f of b minus f of a. This is where we use the lookup chart for the normal distribution, which I gave you last lecture. Okay. So the kind of questions we would expect is for a given value of x, or for the chance for x taking a certain range of values. This is the standard. This is the type of calculation. Any questions so far? Does all this ring any bells? Okay. So this is a distribution in which there are two parameters. Mu is the mean and sigma or sigma squared is the variance. Do you have a question? No? So the obvious question is, how do we get these? How do we end up with these two values? Any thoughts? If you're doing a measurement or a survey or sampling or whatever, the act of collecting data, okay, I'll call it data collection. Okay, you would do a certain number of trials. Like if you are measuring voltage, you might acquire like 1,000 samples or 10,000 samples and so on. You will do n trials. Okay, and n is a large number. We typically consider n values which are large, like 100 samples or 1,000 samples and so on. Something that's large comparable to 30, because this 30 is sort of a line in the sand. You consider n 30. These are called small data sets, and these are called large data sets. It's an arbitrary definition, but that's what that is. And whatever we have seen so far pertains to large data sets, which is where our normal distribution operates. And for the small data sets, today we are going to see what is called as students T distribution. This is where the today's material fits in. Okay, so you do n trial. N is like 1,000. Okay, from n trials, how will you get the mean? You will do 1 over n sigma xi, that is mean. And how will you get variance? You can write 1 over n minus 1 sigma xi minus mu whole square. Either the mean and variance are provided to you, or you are given the raw data from which you can get the mean and variance. Once you have the mean and variance and you know the number of trials, you will calculate probabilities assuming a normal distribution. All right. So this is for a mean and variance which come from some data set. Okay. Are you writing this? You're not writing, like, does anybody want me to wait? Shall I erase it? So the special case, when mu is 0 and variance is 1, that is called the standard normal distribution. Standard normal distribution. So here, this comes down to f of x dx equal to 1 over square root of 2 pi exponent of minus x squared over 2 dx. This is the value of 0 to z or 0 to z f of x dx is tabulated in the handout. That is the table of standard normal distribution. So if I ask you, what is the probability of, say, -2 to 1 f of x dx with mu equal to 0 and sigma squared equal to 1, what will you write? This is a real exam question where f of x is given to you as the standard normal distribution. How will you compute this integral? We saw this last lecture. Anybody attempted the mock exams I posted? No? Your quiz is on Thursday. Remind me. So what will you do about this? How will you evaluate? So this is like writing, I have the Gaussian distribution centered around 0. I'm asking for the area between -2 to +1. Yeah.
1 minus 2 divided by 1 for 1 for the 200.
Sorry, say that again.
2 minus 2 minus 0 over 1.
2 minus 0 over 1. No, sorry, that's not correct. First of all, do you see that this is the area between -2 and 1? Okay. The tabulation given to you is only for 0 to z. It is like if z is here, it is for 0 to z. It's tabulated only for that. It doesn't cover negative values. But we know that this function is even. It is symmetric about 0, right? So you would first write this -2 to 0 f of x dx and then 0 to 1 f of x dx. Would you agree? This is like splitting it, this area plus this area. Okay, so 0 to 1 is easy. You can look it up from the table. 0 to 1 f of x dx for the standard normal distribution. I even remember this since we did this so many times. This is 0.3413. You can check. Everybody agrees with me that this is 0.3413. The other one, -2 to 0. -2 to 0. I did this, so instead of repeating everything, I'll just say -2 to 0 f of x dx is equal to 0 to 2 f of x dx. Like, since this is symmetric, it's almost like putting my hand here and flipping the page, and it would fall here at 2. So -2 to 0 is same as 0 to 2. So this value here, if you can look up and tell me, what is it?
0.4772.
0.4772. So -2 to 0 is 0.4772, and then 0 to 1 is 0.3413. 5, 8, 11 carry over 1, 0.8185. If this solution process looks like, you understand this, you are okay for Thursday. If this looks like totally new and you are lost, it's going to be a rough ride. Okay, this is all we did last time. Okay, none of this is new. So you can go back and watch the lecture. So this is for a special case which we call standard normal distribution. the last concept we saw is what if we are not dealing with a special case, but mu is any arbitrary value and sigma squared is also non-zero or not equal to 1 in general. Then what happens? So here you have this distribution. The step to follow is use or substitute z equals x minus mu divided by sigma. So f of x dx becomes f of z dz, which is equal to 1 over square root of 2 pi exponent of minus z squared over 2 dz. This substitution takes care of this. So after you did the substitution, suppose now, if you're done writing this, I'll give you a different problem, like a different example. Can I erase this part? Okay. Okay. I might be giving this example also because I might remember this from preparing the test. So please pay attention. So let's say mu is 10 and sigma squared is 1.1. Okay. I want to calculate what is the probability that x takes values between 8.5 and 11. X takes values between 8.5 and 11. X is a random number. X is a random number with mean mu and variance sigma squared. So what do I do first? X equal to, z equal to, z, introduce a new variable called z, which is defined as x minus mu divided by sigma. So you have to go from x to z. If x is 8.5, z is 8.5 minus 10 divided by sigma squared or sigma square root of 1.1. Can you compute and tell me this number? Negative point? Negative 1.43. And if x is 11, this is 11.0 minus 10 divided by square root of 1.1, which is
0.9535.
0.9, we'll call it 0.96. So the probability that x, which has a mean of 10, okay, mean is 10, and a variance of 1.1, falling between 8.5 to 11, that is this area. This is same as or equivalent to z with a mean of 0 with an adjusted mean, that is mu of mean is the standard normal distribution is 0, variance is 1. So this is same as probability of this between 8.5 to 11 is same as probability of z between minus 1.43 and 0.96. These two areas are the same. So I write probability of 8.5 less than x less than 11 is same as probability of minus 1.43 less than z less than 0.96. This is f of 0.96 minus f of minus 1.43. Sorry, yeah, this is f of minus 1.43, which is nothing but f of 0.96 plus f of 1.43. Same logic, I'm writing this as minus 1.43 to 0 f of z dz, and then 0 to 0.96 f of z dz. You don't have to do anything about this except look it up for 0.96. This is nothing but 0 to 1.43 f of z dz. So look up for 0.96, look up for 1.43 and add it up. That's your answer. Can you tell me the values?
3.5, 0.96.
Plus 1.43.
0.4236.
11, 5, 5, 7, 0.7551. That is your answer. That 7551 or nearly 75.5% is the chance that x will lie between 8.5 and 11. Still recapping, still not like getting into the new content. Okay, one more concept we saw, which is, are we good so far? Calculating probabilities for standard normal distribution and any normal, general normal distribution. Okay, mu and sigma squared are any values, not just 0 and 1. All right. Next concept we saw is called confidence interval. What is confidence interval? Something not clear? Something not clear?
What did you say that this one was called?
This is
If you have to change the,
this is a transformation. That is, this transform z x to z using this substitution.
but it's still just a probability.
Yeah. So okay, this is any or generally normal distribution, and if mu is 0 and sigma squared is 1, that is called standard normal distribution, which is what is tabulated in that sheet, which will be provided to you in the exam. Yes, what were you going to say?
Yeah, just, I guess the method is standard normal distribution.
Yeah.
Okay.
You're at the end of the day reducing anything to the standard normal distribution and then solve. Okay. Okay, so the last concept that we saw under this topic, by the way, all of this that I'm talking now is fair game for tomorrow's quiz or Thursday's quiz. Only the stuff that I discussed today will be in the exam. Okay. All right. So if you do n trials, okay, and from that you get a mean which is 1 over n sigma xi over n. Okay. You also get a variance sigma squared, which is 1 over n minus 1, I equal to 1 to n, xi minus mu whole square. Okay. Just because you got an average doesn't make that necessarily the true value of the quantity. What we say is the true value can be found with P% probability in an interval termed the confidence interval that is centered at the mean value. So I'm talking about the true value of x can be found between mu plus minus ci with P% probability. So if I say here is the mean, the true value can be found within one confidence interval on either side. Question is, how do we get the confidence interval?
Second x minus mu for complex interval.
Right. You would take, first of all, you have to figure out with what probability or what level of confidence you want to determine that interval. Do you want 95% confidence or 90% or 50% determines what P is. Commonly we take P to be 95%. Okay. If you take 95%, what is the implication? I have my bell curve. Here is mu. Okay. And the true value I'm saying is between mu plus Ci and mu minus Ci. Okay. And this true value I'm saying is to be found with P% chance, and P happens to be 95% as my choice. So it's like asking what values of this mu plus Ci and mu minus Ci, what value of mu plus minus Ci contains 95% of the area. How will you answer that question? How will you answer this question? How do I determine? So it's like saying, in putting it in words, integral mu minus Ci and mu plus Ci f of x dx is equal to 0.95. That is the statement.
D equals 1.96, negative 1.96.
So you are saying that if this integral is to be 0.95, let's say you effect a transformation z equals x minus mu divided by sigma. Okay, so if I substitute, if I have to go from x to z, I'll write mu minus Ci, which will be z will be minus Ci divided by sigma, and then mu plus Ci, which will be plus Ci over sigma. Check this and you all tell me if this makes sense to you. All I have done is do a transformation of z equals x minus mu divided by sigma, and this is how the limits will change. So this is like saying minus ci divided by sigma plus ci divided by sigma f of z dz equal to 0.95. Look at this. Take a minute. Tell me if this step makes sense. So this graph here, it's like writing 0. I have minus ci divided by sigma plus ci divided by sigma, and I'm saying within this range 0.95 or 95% of the values are to be found. All I have to do is look up in my lookup chart to see what value of this will lead me to 95%. Right? So if I write this becomes 2 times 0 to ci divided by sigma f of z dz equal to 0.95, or 0 to ci over sigma f of z dz equals 0.475. All you have to tell me is, you already did, is what value of the upper limit of integration will lead to 0.475. All of you, please look up that table and answer this for me. I gave you the handout. I didn't bring extra copies today, but I hope everybody has one. So look at the tabulation and see where is 0.75 and what value of z will lead to 0.75 or 0.475. Yeah. 1.96. So 2 people have confirmed 1.96. I want all of you to actually do it and confirm to me that you are also able to do that. Are you able to? Are you? Did you? Yeah. Have you? So here is the table. So I'm looking for 0.475, half of 95% or half of the probability level. If I do this, I get 4750 here, which is in the line 1.9. And if I scroll up a little bit, it happens to be 1.96. So here is 0.06 and here is 1.9. So z value is 1.96. That is equal to ci over sigma, or ci is equal to 1.96 times sigma. How do you make sense of that, or how would you state it? How would you interpret it? Let's say the true value of the measurement that you are making is to be found with mu plus 1 point, from mu minus 1.96 sigma to mu plus 1.96 sigma. Just because you got a standard deviation, that doesn't directly mean x, like one standard deviation contains your truth. Truth is contained in this interval with 95% chance. If you wanted 99% chance, the interval would be wider. If you are okay with 50% chance, the interval would be narrow. So if you figure out or if you master this process, this step right here in the exam, I might ask you 90%. And if it is 90%, this is half of that is 0.45, and this will be 0.45. And what value of z will be that? Look at the table and tell me. It's between 1.64 and 1.65, right? So we'll say 1.645. This will be 1.645 sigma. This is all highly okay with 95% probability. This could be on the test. The manner of speaking. Yeah.
1, 2, okay.
Oh, this is because I have minus ci to plus ci. I write it as 2 times 0 to ci. That's where the 2 comes from. I mean, it's like asking what is the area between minus ci and plus ci. It's nothing but 2 times 0 to ci.
You're saying it's the same.
It's symmetric. Symmetric about 0. Because normal distribution function itself is symmetric, it's an even function. This first 40 minutes that I spent is a summary of everything that's gone on so far. Okay. Now the last concept in this topic, I also told you that we'll do a simulation of the election outcome, which we will do after the quiz. Okay, on Thursday. So that is not obviously going to be on the quiz, the Monte Carlo simulation. All right, drop your pencils, listen for a moment. Any act of measurement involves repeated trials. You get n data points. From that, you get mean and variance. Everything we saw so far pertains to large data sets where there are large number of observations. So you get a certain level of statistical accuracy just by adding. What happens when you don't make 30 observations or more? In fact, you make very few observations. Let's say you are trying to take a pressure reading. Maybe you do that 4 times. You get x1, x2, x3, x4, or p1, p2, p3, p4. Then you can still calculate a mean value. Okay. So whatever we did for large trials, we'll call it population mean and population variance because they are for the population entirely. If you are doing a very small number of observations, so from now on, our discussion is to the left of 30. Keep that in mind. Small number of observations. Okay. So let's get rid of this normal distribution. If there is an important concept I want you all to take from the statistics, it is this concept which we will be using very much in your lab courses. Okay. So you make a small number of observations. Small number of observations or trials where typically n is less than 30. So you can calculate a sample mean which is 1 over n sigma I equals 1 to n xi. Same as before, except it's called sample mean because it is for a small sample, like a very small number of observations. You can also calculate a sample variance which is 1 over n minus 1 I equal to 1 to n xi minus mu, or I shouldn't use the word symbol mu. I'm going to start using the symbol x bar. Xi minus x bar squared, and for variance or sample variance, I'm going to start using the symbol sx squared. Okay. We still want to ask the same question. you made 4 values or you took 4 values of pressure. How do you tell what is the true value? We'll say the true value can be found with P% probability in an interval termed the confidence interval that is centered at the mean value. Everything remains the same except this CI determination, the CI now does not come from a normal distribution. Normal distribution is only for large data sets, not for small data sets. I want you to write it down until here, okay? We are going to write down an expression for CI, which is different from the previous case. Write it up to here. So start here, right up to here. All the ideas of confidence interval are the same, except a different formula for confidence interval is going to come up. In the exam, I won't give a problem statement and say, use normal distribution table, use the other table. I won't say anything. The only clue for you is, I'll say the experiment involved n trials where n equals 27 or n equals 540. So you will have to think, if it's a large sample, I need to think normal distribution. If it's a small sample, I'm going to think student's t distribution. This is your clue. There won't be any other indication. And it is a trap. It is to trap the folks who are not paying attention. Okay, so do you have it down up to here? Okay, so I'll write a few sentences which are like details. The first detail is small data sets are modeled using the so-called student's t distribution. The idea of student's t distribution goes something like this. Think of that experiment where you are taking n equals 4 values of pressure. You're taking 4 values of pressure. Suppose you are doing an experiment and you also are doing an experiment. Okay. So you got one set of values, P1, P2, P3, P4, from which we'll get sample mean P bar. I'll call that P1, or I'll call it Parker, right? P Parker. It's the mean value that Parker got. What is your name? Tim. You also repeat the experiment. P1 dash, P2 dash, P3 dash, P4 dash, and you got a mean, we'll call it P from Tim. You can easily see each of you will get a different value. You are all measuring the same pressure. Let's say you take turns with the transducer. Each of you acquire 4 values and you can get any number of sample means. Okay? You don't bring to me the values. You just bring to me your mean value. For you, the truth is your mean value. For you, your mean value. For you, your mean value. I get like 10 values of the pressure, mean values based on 4 data points. Are you with me in the story so far? So now the question is, how do we come to a determination what the truth is? This is the measurement question. The student's t distribution is built on the premise that if you are taking a data set, and if you repeat the data collection n number of times, each time you will get a certain mean value. The student's t distribution assumes that those mean values themselves follow a normal distribution. So here's a class of 10. Maybe I will have a class of 40. I'll get 40 mean values. I'm supposed to think that those 40 mean values will themselves follow a normal distribution. So I'll get sort of a mean of means. Okay. And then based on that mean of means, I can come to a estimation of what should be the confidence interval. This is the flow of thought. A small sample can be taken many times. If you aggregate those individual samples, from that you can get a mean value for the entire distribution. So sparing you the details, I'm going to write CI. This is the all important formula. CI is sigma times the t statistic evaluated at p% probability and for a certain degrees of freedom divided by square root of n. Of course, we are skipping the derivation. You all young kids, you love your phones, I know, but at this stage, this is the one place, this 90 minutes is when I can really escape the outside world. I don't want no calls. I don't want to hear about any trouble. I don't want to know if the dishwasher is broken. I don't want to know if the pump is broken. No, this is my time. I even tell my wife, when I am about to die, I want to die in my classroom teaching so that I won't feel the pain until it happens. All right, so this formula comes from magic because I skipped the derivation. I just threw it at you, but the flow of thought is if you repeat an experiment with n trials many number of times, those individual samples themselves follow a normal distribution and will help you arrive at this confidence interval formula. Sigma is the sample standard. Sorry, I should write sigma. I should write Sx. Sigma. I should use x bar and Sx. Sx is the sample standard deviation given by this formula. So if you did 4 observations, you will get a sample standard deviation with those 4 observations, where n is 4. Example. Okay. And here n is 4, here the denominator will be 3. What you need to learn is what is this t value? This is the unknown here. This is the new thing that's coming up. This t value this t value, t of p comma nu, is called the t statistic. It's sort of like the 1.96 value. Okay. And P is the probability level. And nu is the degrees of freedom, which is equal to number of observations minus 1. Why we say n minus 1 is you have only 4 observations, right? From that, if you calculate a mean, that means all 4 of them can no longer now be independent. You have reduced it to a mean plus 3 independent values. Because if you specify mean, out of that 4, one of them is taken away. So it's like writing P bar is P1 plus P2 plus P3 plus P4 divided by 4. I can specify 1, 2, 3, 4, or I can specify P bar, P1, P2, and P4, which means P3 can come from this equation. So when you go to sample variance, the number of independent observations is not n anymore. It's now 1 less than n. That's why we put n minus 1. And that is why this n minus 1 appears here. I'm going to show you another lookup table. So another lookup table for t values. Okay, so let's put up the table and then talk. All right. Listen, okay, I'll show you some feature. Then you can continue writing. We'll do some problems. So look at the table here. Look at the third column. Okay, T95. Let's focus on that T95. That is like saying if I have a probability level of 95%, I will look at the third column, T95. Degrees of freedom starting with 1. Like if you made 4 observations and degrees of freedom is n minus 1, nu is 3. Or if you made 10 observations, degrees of freedom is 9, nu is 9. So it's always 1 less than the number of observations. Okay. And if you scroll your eye through the list here, okay, nu starts at 1, goes up to like infinity. What is this value z? This value here at infinite number of observations? 1.960. It's the same 1.960 which you got from a normal distribution, which is the large number limit of the student's t distribution. So this is one place where the two distributions coincide. Okay. The other feature is, remember I told you the confidence interval I told you the formula. It is Ci equal to t statistic at p comma nu multiplied by sigma divided by square root of n. I didn't tell you where it came from, but here is the formula. So if you are thinking about the confidence interval, if you make a lot of observations, that is, if you make a large number of observations, what happens to Ci?
It's small.
It becomes arbitrarily smaller because if you did 100 observations or 10,000 observations, this becomes very small. That Ci itself will go to 0 in the limit of a large number of observations. You see that? So any good experiment would try to go for many observations so that the Ci can be made smaller. What is the use of making Ci smaller? It means you can tell with certainty your true value is in a very narrow range, that your measurement is almost can be taken as truth. Almost, never fully. The other observation is, here is sigma in the numerator. You are observing a pressure, let's say you're measuring pressure in a cylinder. Let's say the pressure is really steady. What happens to sigma as a consequence? If some quantity is very steady, the standard deviation would be large or small? Small. And if the pressure is unsteady, suppose for example you're sticking out a pressure transducer on a windy day, the pressure keeps fluctuating, you get 4 values, that sigma will be higher than in a quiet air, like in this room. So sigma can be thought of as something that contains the physics of your, or the rate, or it is inherent to your measurement and not how you do the measurement. You could stick out a velocity probe in a laminar flow or a turbulent flow. You will get a large sigma in a turbulent flow, whether you take 10 samples or 200 samples. So sigma really comes from the measurement situation. The other two factors are really to compensate for that, in the sense, okay, you are measuring a turbulent flow, you get a certain 1 meter per second velocity. Okay, certain 1 meter per second velocity. What is the true value? Is it 1 meter per second plus minus 0.1 or 1 meter per second plus minus 0.5? Because I have a high fluctuation, does that make my measurement less reliable or more reliable? That is the question. You could have a high standard deviation. How do you compensate for it? You increase the reliability of your measurement by making more observations. And one thing you can see in this chart is as you go down in this column where nu is simply equal to n minus 1, as nu increases, the t value also decreases. So if you see here, it starts at 12.7, goes down to 1.96. So you can make your measurement more reliable by doing more observations, which will decrease the confidence interval and also decrease the t statistic value. If I ask you to measure the pressure in a gas cylinder, you come back with only 2 observations, and you come back with 6 observations, like 6 trials, 2 trials. Whose measurement is likely to be more reliable? Whom should I rely on without thinking about the human factor? More observations, because more observations mean square root of 6 will make this narrower than square root of 2. Suppose you did 14 observations, 2, 6, 14. Obviously, 14 will give me better estimate. So, in summary, you can do an experiment with any number of trials, n trials, let's say. You can easily get a mean and a standard deviation. The confidence interval idea is to say how reliable is my mean. That is why the name is confidence interval. How much confidence can I place on this measurement, and how wide is the range in which the true value is likely to be found. And that range is given as the product of 3 factors: the t statistic, which accounts for all the statistical variations; the sigma, which is like a inherent to your particular measurement, because it could be a turbulent flow or a laminar flow, it could be a very steady air versus turbulent air, something like that. And square root of n is just how many data points that you acquire. As in general, you can just say more measurements means more reliable. Okay. So the type of questions we are interested in this is, we give you a problem. Okay, let me show you an example problem here. Just want a simple example to show you. Yeah. All right. So look at problem 4.49. The following results are obtained with 10 repetitions of loading in centimeter. Determine the mean value, the standard deviation, and the best estimate of the true value for this data set. Over what interval would 50% of the entire population of deflection values fall? We'll come to the second question later. First question is very typical of what we want to be able to solve. Get the mean value. How will you do that? 10 x values, how will you get the mean? Add them all up, divide by 10, right? Please do that. Let's do this problem. Get the mean value, very easy, straightforward. So I'm going to use Excel to just keep it easy and quick for us. All right, so data. All right, so what's the mean value? Average. Okay, 5.613 is the mean. So I'll write it here, mean, or I want to call it sample mean. And before that, I'll also write sample size n. N is 10. Sample mean, I'll call it X bar. Okay, and then sample standard deviation, or sample standard deviation, we call it SX. So if you go to Excel, you can write standard deviation, and then see here standard deviation dot p, calculate standard deviation based on the entire population given as arguments. And then second line is standard deviation S, which calculates based on a sample. Our sample happens to be just 10 values. So we'll select the second option of these quantities. So that is 0.626265. Question to you, how will we get the true value is what is asked. What is the best estimate of the quantity being measured? Or in other words, what's the true value? So we want to calculate the width of the confidence interval, which is t statistic multiplied by Sx divided by square root of n. Okay, so Sx is given as 0.62. So this is 0.62 divided by square root of 10 or n. And then I also need the t statistic, which I'll say is in this cell right here. So the t statistic needs to be looked up. And to do that, we'll bring this table back. I know I didn't bring a printout, but you could still look up the table. Yep. So here is our table. So I want you to look up the t statistic value for 10 measurements at 95% confidence. So if you did 9 measurements, sorry, 10 measurements, your degrees of freedom is 9, and you want to look up at 95% confidence, which is 2.262. This is the skill, like in the sense, reading this chart is needed for you to solve the problem. Okay, so I will say 9 degrees of freedom, 95% confidence is 2.262. This chart will be given to you for you to do this. Okay. So if I take 2.262, put it in here. Oops. 2.262. And then I have t statistic multiplied by standard deviation divided by square root of number of observations, sample size. 0.448196. Problem doesn't end here. Then you have to say the best estimate of the measured quantity is 5.613 plus minus 0.448 at 95% confidence. This is the best estimate. If you want, question for you, if you want to target a certain value for this 0.448, how can you go about it? How can you make it narrower? Say I want it to be 0.1, 5.163 or 5. Whatever the need is. Plus minus 0.1 is my targeted confidence interval.
So the confidence percentage, so that it'd be TS would be lower.
You are an excellent candidate for Boeing. The moment I asked you for more confidence, you went about cutting the number of instead of making more observations, you went for lower confidence. What else can you do? That's a valid thing. But what else?
More samples.
More samples, because the confidence interval scales with square root of sample size. Right? So if you make, instead of 10 observations, you did 20 observations, you would be getting a better confidence estimate. And you can target, you can keep increasing it doesn't actually, that's a great question. For the same set, assuming the sample mean remains the same and standard deviation remains the same, how many observations should we do to get 0.1 from 0.448? That is, I'll keep this n blank. Okay, n is blank, same sample mean, same sample standard deviation. What value of n will lead to a confidence interval of 0.100 at 95% confidence? Can you answer that? Like, tell me what will you do? How many observations should we make to reduce the confidence interval? If you want to reduce, should you increase the number of observations or decrease? Increase, right? Question is by how much? So you can do this with a little bit of trial and error. Suppose we did 20 observations. What is the t statistic for 20 observations? Can you look up and say, can we go back to the lookup chart? If we did 20 observations, which is 19 degrees of freedom, and the t statistic is 2.093. Okay. Everybody agrees it is 2.093. Right? So I'm going to go back and write this is 2.093, and the formula will tell me this is 0.62 times 2.093 divided by square root of 20. So from 44, I have come down to 29. Okay. If I frame the question, what value of n will lead me to 0.30 approximately, we are done. If kind of 30 is my target, 20 observations will pretty much get me there or within that. Okay. If I just say, how many more measurements are needed to get a confidence interval of 0.25 at 95%? So I'm targeting 0.25 this time. Let's say I try with 30 measurements, same mean, same standard deviation somehow. What is the t statistic for 30 observations at 95% confidence? So I have 21 and then 30. as you go for larger values of the degrees of freedom, this changes very, very slowly. You can see that from 20 to 30, the jump was hardly noticeable. Between 60 and infinity, the jump is even like less pronounced. So we'll just say we'll go with 30. Okay. So one thing you got to remember is when you're dealing with this table, you have to be making reasonable approximations. This table ain't precise. It's not built for like continuous values. So you have to be making some jumps. Okay. So I have 30. I have 2.042. Okay. I'll put 2.042. And then confidence interval is 0.62 times 2.042 divided by square root of 30. 0.23. So I am within that 0.25 band by doing 30 observations. So if I'm your supervisor, I'm saying we need to get this part measured to a confidence level of, if this is 5.6, I can only tolerate 5.6 plus minus 0.2 or 0.25. I'm going to be giving you that constraint and you are going to be designing how many measurements should you take. Should I do 20? Should I do 40? The answer is right here. Okay. So the best estimate of the measured quantity is this. You can also write this as the true value can be found in the range 5.613 plus minus 0.448 with 95% confidence. That is also another way of stating the answer. This is what you are going to get not on Thursday, but almost certain that in the exam, a question like this is going to come because the quiz already tests you on the other parts. I'm going to post this Excel sheet for you to try later. Okay. So this line here has the formula. Step 1, compute the mean and standard deviation for the sample. Use the correct formula. Step 2, look up the t statistic. Step 3, get the confidence interval. Step 4, write a closing statement. You're done. If you want, I'll even tabulate that here. Step 1, compute sample, mean, and standard deviation with the correct formulas. That's important. Step 2, look up the t statistic. Pay attention to degrees of freedom equal to n minus 1. Step 3, compute the confidence interval. And step 4, answer the question with a closing statement. The question could be something like, okay, we did 10 measurements. How many more measurements are needed to get a CI of 0.25? The answer could be, you did already 10 and 30 gets you within 0.25. The answer is then 30 minus 10, 20. How many more? You already did 10, you ended up with 0.448. How many more do you need to get within 0.25? The answer is nearly 20 measurements, additional measurements. Okay. Questions? Ask something if something's not clear.
You're not necessarily finding the exact number.
Yeah, these questions are always what value of n will lead to a confidence interval of 0.30, which is like saying mean plus minus 0.30. If you happen to get mean plus minus 0.27, that still technically satisfies this. So it's an upper bound. So if you get within, that's okay. In the exam, it's not possible for you to try everything from 10 to 30 in increments of 1. You have to, like your bisection method, you have to guess a little bit. So it's a. So the main formula that I kind of parachuted into this whole conversation is this one here. When you did the normal distribution for large data sets, we went through the derivation to say Ci equals 1.96 sigma. Here we didn't do any derivation, we just wrote, oh, it's equal to t statistic times sample standard deviation times square root of or divided by square root of n. How? We don't care. We really don't. We just brought in that formula and I'm asking you to use it. Okay? So shall we do another quick example or you have any questions? Shall I? Okay. Problem 4.51 is basically the same thing. Just for practice, can we do that? You have 7 observations, 43, 50, 53, 47, 31, 51, 49. Determine the mean and its confidence. Basically saying determine the mean and the confidence interval. Okay. So 7 values. Copy that. In the exam, you won't have Excel, remember that. So problem 4.49, problem 4.51. So I have 7 values. I'm going to copy some of these here. All right, what is my sample size? Sample size 7 observations. Sample mean, I can do this, but in the exam you can't, remember that. That is the sample mean and then sample standard deviation. Have this. Now I'm going to bring up the t-statistic table, which you may also have on your laptop. I want you to look up and tell me the t-value while I keep quiet. So here is the table, 7 measurements or 7 trials and 95% confidence level. What is the t-statistic value you need to take from here? Choice A, 2.365. Choice B, 2.447. B, because you're paying attention to the degrees of freedom being n minus 1. Especially for small values of n, it's important because if you took 1 instead of 2, there's a huge penalty for that. But later the penalty goes away. If you took 30 instead of 29, doesn't matter. Right? So 2.447. Okay. So that is our value for 6 degrees of freedom and 95% confidence. 2.447. So the confidence interval is t-statistic multiplied by standard deviation divided by square root of number of observations. So this is like writing the true value of the quantity is 4.63. If I do 3 significant figures times 10 power minus 3 plus minus 0.0 wait, I wanted points plus plus minus 0.0689 times 10 power minus 3. 06 or 006? 06. If you just forget this exponent for 1 second, it's like 4.63 plus minus 0.06. Okay. What did I miss in this statement? For the statement to be complete, I left out one thing. Confidence level, very good. At 95% confidence level. Just for perspective, if you take 0.0689 divided by 4.63, that is 1 times 100. I'll also multiply by 100 times 100. That is 1.48% or nearly 1.5%. Nearly 1.5%. I'm saying my true value is 4.63 plus minus only 1.63%. I'm sorry, 1.5%. That's pretty good because whatever mean I'm getting is practically the true value because the width is very small, only 1.1%. If you get a width that is 50%, it's like saying your height is 6 feet or 4 feet. That is really no information to say such a wide confidence interval. The goal of any measurement is to narrow it down to as narrow as possible. There could be factors like time, cost, limitation of instruments or resources or personnel, which can limit you in getting more measurements. But always the goal is to get more measurements. There could be funding limitations or time limitation, or you might, to get a sample, you might have to go to Antarctica or something. So you can only get 4 samples. There are so many limitations, but the idea is to make this as small as possible. So for Thursday's quiz, I already put out mocks, 2 mocks. Please go through them. You should be able to do those. I have prepared the exam, so I know what's going to be on there. It doesn't include any of today's stuff. For the next lecture, first 40 minutes is quiz. Next 40 minutes, we'll do that programming exercise, which if you finish and submit will count towards your homework. And for the exam, I want to hold a virtual session where we can review all the topics from the beginning. Would Friday 3 p.m. be okay with everyone? I'll post the record. Friday 3. How many of you can guarantee that you will attend? Only one. What time will work for others? Just asking.
Because Thursday might work better, Friday's just like a lot of your problem.
5 to 6? I can't do 5 to 6. I'm a man with 2 kids. So Thursday, what times will work?
Maybe like in common.
Any chance 1 to 2 will work? Right after class.
I don't know.
Okay, what about others? How many can do 1 to 2 on Thursday? 1, 2, 3, 4, 5. Can't you? So I can work with 5. If 5 people show up, we can discuss and do a recording that I can post later. Because I really want to give a short list of topics to ask you to study, because we already went through the quizzes and I asked questions. There are topics I didn't cover in the quizzes, which I want to cover in the exam. So I want to focus a little bit. Yeah. How many can make it work before class? You are not available. You? No. Like if we do 10:30 to 11:20, Not work? Okay, so the choices are either Thursday before class or after class. That's our choice, right? How about half an hour before and half an hour like an extended class? Like if we start at 10:50 and go on until 1:15, will that work for most people? Oh yeah, yeah. Let's do after. Okay, let's do after. We'll do 1 to 2 and I'll try to post the recording immediately. Okay, so Thursday, 1 o'clock, we are planning. Let's just finish the class, take a quick break and assemble at 1 o'clock. Okay, thank you. And this is voluntary, okay? I'm not forcing you to attend, so don't go and complain to me that, no.